So let's go ahead and look at another example of calculating entropy change. We're going to move on from the molecular basis and look at some of the examples that we talked about at the beginning of the chapter. So we had this example where we had gas on one side and it's empty on the other. And if we open this, we know that our system is going to go to a state where the gas is spread out on both sides. Now, if we want to calculate the entropy change here, we need to calculate it for a reversible process. Even if the process is done irreversibly, for example, if we just open the valve and let the gas expand, without doing it slowly and reversibly, the entropy change for the system is still going to be the same, regardless. So we can look at, and let's imagine we do this also at a constant temperature. So do a reversible isothermal expansion. So du is equal to dq reversible plus dw reversible. We'll start with the first law and then use that to get our entropy change from dq reversible. Okay, so because we'll assume ideal gas behavior, you can always assume that unless we explicitly state otherwise. We know that du is equal to 0 because the internal energy only depends on temperature for an ideal gas. So we can say that dq reversible is equal to the negative of dw reversible. And the reversible work is equal to minus pdv, so negative of it is positive pdv, which means we can go ahead and change this to nRT over v dv. Okay. So then we can substitute that into the definition of ds is equal to dq reversible over t. So if we want delta S for this process, we need to integrate this. So integrate nRT over v over t dv. All right, temperature is going to cancel. We need to go from volume 1 to volume 2, so our gas is expanding from just being on the left-hand side to moving to the right-hand, to both. So V2 will be, approximately twice V1 if these are equal size. And so ultimately we get nR log V2 over V1. We've already done that calculation before, so this should look familiar. Okay, and so this is delta S, where we could say this is for the system. Now, we could do this process in two different ways. We could do the reversible process, where we're slowly letting gas out and this system stays at equilibrium essentially. And so the pressure slowly builds up on the right-hand side. Or we can just open the valve up and let the gas expand against zero pressure. And the entropy change will be the same either way for the system, because entropy is based on the reversible process. All right. So what's the difference? What's the difference between the reversible and the irreversible case? Right, because entropy is a state function, we will get the same delta S whether it's done reversibly or irreversibly. And the key difference here is what happens with the surroundings. All right, so in the reversible case, we know that delta S for the overall system has to be equal to 0. So there's going to be some heat transfer between the system and the surroundings to keep things at constant temperature. So that means that delta S for the system we calculated is nR log V2 over V1. Delta S for the surroundings has to be equal and opposite. So it has to be minus nR log V2 over V1. Right, so overall this has to work out to be 0. In the irreversible case, if we let the gas expand against zero pressure, P external, rather than balancing out the whole time, is just going to be equal to 0. So we can say that dW, irreversible, is equal to 0, which also means that dQ, irreversible, is equal to 0. There will be no heat transfer because the gas is expanding against zero pressure. So delta S total will be equal to our change in S for the system, nR log V2 over V1, plus our change for the surroundings. In this case, that's 0, because there's no heat transfer happening here. And so overall, we get delta S is greater than 0, because the gas is expanding, this first term will be positive. And so we get a case where, right, so this gives us the fact that our total entropy change for system plus surroundings is different for these reversible and irreversible case. That's what makes them different. But the change in entropy for the system is the same because it's a state function. So that's an example that is talked about in your book. There's a couple other examples you can look in your textbook for, mixing two ideal gases, the entropy change in that, and also putting two pieces of metal at two different temperatures together, showing that in those cases, as the process happens, we get an overall increase in the entropy of the total universe, right? If we think of the whole isolated system as being the surroundings plus the system, we get an overall increase in entropy.